today, and so let's get started. So this work is done with my former student Sung-Cheng Lu, who recently moved to Perimeter as a postdoc fellow, and you can read about this work here, and we synchronize our archive posting was posted on the same day with work with Matthias and collaborators, and you will hear Matthias talk, I guess, next talk. And there's overlap, but the overall our focus was fairly orthogonal. So I will encourage you to read both papers. All right. So let's get started. So let me motivate the whole talk by that's a very general question. What is the landscape of time-evolved many-body states? So consider like the usual quench protocols. So start from some low complexity, low entanglement state, let's say size 0, and evolve the system, and ask what are the universal properties of the system at very long times. And this is a very fair question to ask, because when we study ground states, for example, or in more generally states within, let's say ground states, we find very rich class of phenomena, Fermi liquid, superconductors, and so on. Is such a richness in quantum dynamics. So the main thing I want to emphasize is that it's not as easy to find new things with quantum dynamics as with just ground states, because quantum chaos, if it exists, tends to make things somewhat super universal and makes it hard to find completely new things. So why is that? This is this notion of eigenstate thermalization, which tells you if a system is chaotic. I really actually mean I should use the word ergodic to be precise. Then a small subsystem of a large system behaves as if it was in a thermal equilibrium. So you have some closed system. Look at a small subsystem. It behaves as if it was coupled to a heat bath. And if something is coupled to a heat bath, we kind of know what happens. At least there's typically no coherence in the time direction at long time. So this system is fairly incoherent. So which makes finding very different, very new kind of phenomena hard. So here's one kind of a demonstration of that, just to kind of show you how it works. This ETH. So let's say you have some spin chain. There's some non-integrable system. Divide the system into two parts, A and A bar. Here A is 6 sites, and total system is 18 sites. And so I'll show you a video when I press the next button, which is that this spectrum here shown here, the blue dots are the spectrum of the thermal density matrix of region A. And so this is the eigenvalue index, and this is the log of the eigenvalues to make basically units of energy density. So now let's see what happens. So I start from some product state, and I ask how does the actual spectrum of the reduced density matrix as a function of time looks like for region A. Start from some product state. So this is what it looks like. So you see that initially there's some interesting equilibration, but soon you basically get thermal density matrix. So this is in fact a way to read off the Hamiltonian. If you don't know the Hamiltonian, and I give you some product state, you can tell what the Hamiltonian is. It's like if you're very lazy and you don't know what your Hamiltonian is, you can figure it out by just time evolving the system and looking at the density matrix. So one way to think about that is to get new physics, which is not dominated by thermal decoherence. One needs to find ways to impede entanglement growth. That has been kind of one way to think about to find new physics. So there are at least two generic ways to impede entanglement growth, which have been found over last several decades. So one is to use a system which has one is to impose some kind of a spatial disorder on the system. So this is a phenomenon of localization. This is on the left side. So I'm formulating it as a quantum circuit, but you can also think Hamiltonian dynamics. So different colors here denote the fact they're different gates, but they repeat in time. So it's time periodic. So this is my circuit, or it could be just a Hamiltonian, like in this one of basically the first paper which started the field of localization. And of course, more recently there has been discovery of many-body localization and so on. So this is one way to make things not ergodic and get something new. Another way, which is this idea of quantum Zeno effect. So the idea is to start from some entangled state and do a projective measurement, and typically it will tend to lower the entanglement, at least for most simplest scenarios. Of course, there's a way to increase also, but the most kind of natural thing that you obtain if you do the same basis over and over again, then measurement in the same basis, then you will, for example, here you project, suppose you measure the first spin, you get up, second spin is forced to be down, this bell pair. And this is also a way to, if you have, I don't know, if your cat someday is trapped now in this Schrodinger contraption, this is one way to actually save maybe your cat's life. I don't know. If you open it once and you see that cat is alive, just keep watching it over and over again so that system doesn't evolve. So this was this proposal in this paper to save your cat, that you just keep watching it with loving care. And it's one of the first papers on the Zeno paradox. So, but this is okay. This is maybe. So what is the many-body analog of this? Not like directly going to Schrodinger cat, but more, something where there are many different states, not like just two cat states or something. So this is this recent interest in this constructing circuits. This is all these figures are from this work by Leechen and Fisher, where you have some unitary circuit and you put some extra projections in between. So that you sprinkle some projective measurements throughout the circuit. So there's in this case, they studied random unitaries with some local Z measurements. And the more projections you do, the lower the entanglement. So this is the entanglement plot from their paper. If you don't do any measurement, then entanglement is, is maximal possible. And then you keep doing, increase the measurement. What you find is that for small enough measurements, entanglement remains volume law, but the coefficient of volume law decreases from its maximum value. So entanglement entropy density is not maximal anymore. It keeps going down, and at some point, some critical value of the density of this measurements, you go to a sub-volume law state. In this case, an area law state. So this is a volume to area law transition at long times as a function of density of measurements. On that note, I may just very quickly mention in the case of the many-body localization, if you evolve with a circuit at long times, you always get volume law, irrespective of whether you are in the localized phase or the delocalized phase in the time walls wave function. But in the delocalized phase, you get the entanglement maximum allowed by all the symmetries, and in the localized phase, the coefficient of volume law is not maximal. So, all right. So Another related recent progress is to evolve the systems with non-Hermitian Hamiltonians. So no randomness in any way. You're not doing any measurements. So make Hamiltonian, let's say, non-Hermitian. Then also you can have a transition from volume to area law. And this is at least conceptually similar to Zeno effect, because one of the terms in some sense is trying to project to the ground state of this non-Hermitian part. Other term is trying to just generate entanglement. So this is also a competition between projections and unitary dynamics. And this is recent work again, which shows this volume to area transition in this non-Hermitian system. So this is plot from their figure. So there is a one when you don't have much non-unitariness, you get volume law, and then you increase the non-unitariness, then non-hermiticity, then you get area law. So these are two very generic ways. Of course, there are many other ways that have been discussed, which are like, for example, integrability or scarce states or special kind of maybe automatas of some kind, but they tend to be other methods tend to be a bit, let's say, fine-tuned. These are two generic methods which tend to obstruct entanglement. So if I compare these two, this one is always unitary, the localization way of thinking, localization way of obstructing entanglement. This one is at least we don't know any unitary analog, and this requires a symmetry. Localization always requires a symmetry as far as we know so far, and the symmetry is some kind of translation symmetry in the time direction. It could be discrete or continuous. So it is not, I would say, as stable as this one in this sense of requiring a symmetry. And this doesn't require post-selection in the sense that you just evolve it and measure in that final state. You're not doing any measurements anyway. Here, it requires post-selection in the sense that the way to observe this transition is to repeat the experiment, and with a constraint that you get same measurement outcomes over and over again. And because we want to calculate expectation value of some operator in the final state, let's say entanglement entropy or something. So to get that, to calculate and whatever you want to calculate, you want to calculate expectation value with respect to some state, and quantum mechanics is, I don't know, has intrinsic randomness, so you have to prepare the same state over and over again to calculate that quantity. To prepare the same state over and over again require the same measurement outcomes, so the whole trajectory should be same. That's really hard. That's why this phenomena is intrinsically hard to observe experimentally, at least so far. All right. So these are two very different ways. So the main result I would like to advertise here is that there is a relation between these two phenomena, which is obtained by rotating space into time and vice versa. So if you take a circuit, so the arrow goes from MBL to this side. So start from some circuit which produces localization, and then you do space-time rotation, which I will define in the next slide. You will get a new circuit which will have physics of this Zeno effect, and the original transition, which was this MBL transition, will map to some kind of a Zeno transition. All right. So again, these are very special kind of circuits, because here originally you have time translation symmetry in the MBL that will become a space translation symmetry in the rotated circuit. So these are very special kind of many body Zeno circuits which have projective measurements and so on, or non-Hermitian Hamiltonian, but it has this symmetry. So it's not the most general kind of Zeno circuit. So if I rotate space to time as here, you get something like this. So So what is space-time rotation? So let's say there is some circuit which has some, let's say in some basis, it has some matrix elements of this unitary. So you just interchange space and time. Then if you're looking at this way now, then your input legs are z prime and z1 and output are z prime to z2. This is the time direction now, the horizontal one. So this is just the space-time rotation of a circuit. If you're not familiar with circuit, let's say, I don't know, more coming from, let's say, classical mechanics or some field theory background, write down a Lagrangian, let's say, in terms of, let's say, some field theory. I have field as a function of space and time. Just interchange space and time everywhere in your Lagrangian. That's it. So that's basically it. And this has been used. It has become a very useful technique to design interesting circuit for which things can be calculated, as you have already heard in this conference. And this was even in the case of when it is imaginary time rather than real time, it has been actually used even much longer ago to rotate space into time. But that's not as cool as real time, because real time is always harder to calculate things. So here's one example. If you have a circuit which is just identity, unitary, it's just identity, you do nothing essentially. If you rotate it, it becomes a projection into a bell pair. So at least you see how this rotated thing is not necessarily unitary in general. So which is kind of the point of this talk. So why does space-time rotation of localization leads to something like a Zeno effect? So here's one maybe caricature to just think about that. So one very extreme limit of localization is that when you basically remove some of the bonds completely. Suppose I remove this bond. By this bond, I mean I remove this circuit, this gate from my circuit. So then system basically decouples into left and right across this bond. And if I'm removing this bond, basically I'm setting Hamiltonian to 0 on that side. If you at least heuristically speaking, so that's like applying an identity unitary. So if I rotate space into time, that's like applying a projection. So if I think of this direction as now time, then you're applying projection operators in this rotated circuit everywhere. So that will kill the entanglement. So, and it of course is a non-unitary circuit because it has projections in it. Another related motivation is in this amazing work by Thomas Prosen and collaborators. Hopefully, most of you are familiar with this work. They studied a circuit whose space-time rotation gave unitary circuit. It doesn't have any projection or anything. It was again unitary, and they show that it's chaotic, despite the fact that the original circuit was a Floquet circuit with arbitrary amount of spatial disorder in it. So despite that, they show there is no many-body localization in that circuit. So that also hints at the fact if the rotation of a circuit is again unitary, then you don't get MBL in the original circuit. And that makes sense because if the rotated circuit is unitary, in the rotated circuit you have some time-dependent Hamiltonian now, right? Because the spatial randomness of the original circuit becomes the time dependence on the Hamiltonian in the rotated circuit. So if you did find a transition in the rotated circuit, that'll be pretty amazing, because then you're saying that you have a time-dependent Hamiltonian with amazing, I mean, just a random Hamiltonian in time, which has some interesting transition from area to volume law that we don't expect to see. So in a unitary system, so it must be that the origin circuit also didn't have any transition, because the spectral, if you like, trace of the full evolution operator U or the original unitary or the rotated one are same by construction of this space-time rotation. So if one doesn't have transition, also other one doesn't. So anyway, so inspired by these two things, so we start thinking, okay, what if I rotate a circuit which I do know which I happen to know has a localization transition? So instead of working with things which so anyway, that was our thought. So all right, so here's a warm up. So you take some free fermion circuit. After this is free fermion because of Jordan-Wigner, and with probability 0 and 1, you have this HI. HI is 0 or 1 with probability P and 1 minus P. So it's like it has some randomness. And so when P is 0, that is no randomness, then it's just fully unitary. So it's a Floquet circuit. And you can show that when P is any non-zero number, then you get area law entanglement at long time because of this Anderson localization. So now if you rotate it, wherever P is 0, that's like an identity element. No, I mean wherever H is 0, that's like an identity element. So there's some non-zero probability of that happening when P is bigger than 0. So from on those sites in the rotated circuit, because this is identity, it will become like a projection operator. So then you will, in the rotated circuit, you will apply projections everywhere. So if you rotate the circuit, wherever you did not have any H term, you will project in the whole. So it's like you're doing, because of the rotated circuit inherits the translation invariance into time as spatial translation invariance. So you're applying projection everywhere. So that's why you will kill the entanglement completely. And anyway, so this is in this rotated circuit, you will get area law entanglement always. So at least this shows that Anderson localization maps to something in the rotated circuit as area law entanglement at long time because of physics of projection. So that's like a Zeno effect. So this is one simplest demonstration. So the question that's asked, okay, localization maps to this the Zeno effect. If I have now consider a circuit which has a transition, localization, delocalization transition, then perhaps it maps to this Zeno entanglement transition from volume to some subvolume law. So let's see how that works out. So let me demonstrate that for a few examples. So here's the first example, which is a Floquet Arbre-Andre model. So you have some XX term and you have some quasi-periodic Z term. So it's quasi-periodic because the form I've chosen for is HRs, because NQ is irrational number. So this is a free fermion model, and in fact, all the works before there was this kind of a hint that free fermion models do not support this quantum Zeno transition, and in the sense that you don't get any volume law. Let me be more precise. At least there were no known examples where free fermions can have, with non-unitary dynamics, can have, and short-range interactions can have volume law entanglement. So we were not aware of any transition from volume to area law because of physics of projected measurements or any kind of non-Hermitian Hamiltonian. But we know that this original circuit, the unitary circuit, does have a transition. Because we know our Andre model does, at least the Hamiltonian does. So this is a Floquet version of that. So we first look at the unitary circuit. In the unitary circuit, you get three. Actually, instead of you might have thought you get just two phases, localization and delocalization. You actually find three phases. One is the volume law phase. This is the coefficient of volume law at small value of this randomness. At large value of randomness, you get area law. In between, we found is actually a fractal phase where entanglement scales with some fractional power. L to the power some alpha. Alpha is between 0 and 1. So this is a fractal phase. And then you do space-time rotation, you again get actually three phases. The volume law maps to volume law, but now it is the coefficient of volume law is not quantized, but the coefficient of volume law continuously decreases, very much like earlier circuits I showed for the Zeno transition, where coefficient of volume law continuously decreases. And then on the other side, you get two different log law phases. There's the singularity in the coefficient of log here, and both of them have log L entanglement, bipartite 1-on-1 entanglement. And the corresponding transition completely match up. We have a transition here, transition here. And let me just, in one slide, advertise this unpublished work with.
Can I ask?
Sure.
Can I ask one thing about the previous slide? So the limit lambda equals to 0. So this would correspond to free fermionic evolution in the normal unitary direction.
Right.
But then I'm a bit surprised to find a volume law in the of the temporal entanglement, because this problem was studied, I think, by Alessio De Rose and it's probably in the audience. And in their case, they found always an area law. So either
just to make sure, you're talking about a unitary dynamics or the rotated one?
No. So what they did, but he's in the audience, so he can tell you. But they studied the free fermionic evolution in the unitary circuit, and then they look at the temporal entanglement in the other direction, and they found that here you always have an area law. So I mean, this could be consistent with what you find if the point lambda equal to 0 is a singular point.
I think depends on the form of the free fermion. This is XX, so it has C and C daggers. So the whole point is that the original circuit is so the way it works is that so we have an analytical expression for this coefficient of volume law. Because of the fact that the original circuit is unitary, is protecting this coefficient of volume law. So it's possible with some other circuit maybe it doesn't happen, but for this one you can actually show. So.
No, but I mean, maybe is Alessio in the audience, because I think
yes, perhaps I can clarify.
Sure.
Yeah. No, I think the difference is that what Tarun is speaking about is pure wave function, so it's a pure state evolution. While what we look for is a folded circuit, so it's closer to a density matrix, if you wish. So it's
I see.
It's a wave function that lives on the forward and backward Keldysh contour.
I understand.
So it's a bit of a difference.
But so this is essentially Losch-Miteko then. I mean, single. This is not the folded then. Yeah.
Yeah, just the same circuit. If you thought of it as a circuit in the perpendicular direction. So it's no, I'm not looking at any density matrix. Just a pure state.
Yeah, sorry. Okay, so there's no folding. Okay.
No folding.
Okay.
Yeah.
Thanks.
So this intermediate fractal law phase, at least for the unitary case, has been now seen experimentally. So we are very excited about it. So we are working with David Bell's group who observed this. Unfortunately, time is running out. So I should just very briefly say that you can see this intermediate fractal phase in this Floquet circuit of bosons, which is very similar to our original model, and you can study again its rotation and so on. It has these three phases and volume law, fractal, and area law. And the fractal law phase has some transport signatures which are visible in the how the boson cloud spreads. So you put the boson in some lattice, let it expand. For example, in the volume law phase, it expands fast. This is the time direction. See, it's expanding. Area law phase, it doesn't expand. And in the fractal phase, it expands, but at a much slower rate, and it has some exponent this expansion, and you can pull out that exponent, and it's actually most of the phase diagram is actually fractal, which is cool. So, and in the fractal, you can look at even the eigenstates look like fractals. So you go to eigenstate. Eigenstates are not observed experimentally. This is the last thing is numerical. This thing here. If you look, zoom in any portion of the wave function, it looks like you get back the same wave function essentially. It again has similar features. So that's the fractalness of the wave function. And this is very different than the fractal. I mean, so sometimes we will talk about fractal because of some Ray regions effect in MBL, right? You can have, for example, fractal growth of entanglement, t to the power some alpha, but that's because of Ray region effect. Here there are no Ray regions. This is just it's a quasi-periodic system. So this fractalness is intrinsic in the wave functions. So I would like to emphasize that because it's not so far has been seen experimentally or even studied much theoretically in detail. So anyway, so the second example I would like to mention is
I had a question here, if I can interrupt. So in the previous slide, the decay from the volume law to the area law, like where the entanglement interrupt is behaving like a fractal, it's non-monotonic, like it increases and then decreases again.
Yeah, because it has a lot of fractal features, so it will depend on where you are making the cut. For example, because of the fractalness, it has oscillations also.
Right.
So the coefficient of volume law is 0 here, just to emphasize. Because L to the power A, if you divide by L and take L to infinity, coefficient of volume law is always 0. But to really see this exponent A, you will have to plot in a different way, which is in the paper. So to pull out this A. So that's not visible here.
Right.
Yeah.
Okay.
It is not monotonic because that's not, I mean, that can happen. It's not, there's no, yeah. So is that clear?
Yeah, it's clear.
Yeah, we can chat more about this in a few minutes. Since I will. Hopefully, I'll be done in a few slides. So the second circuit which we studied was a 2+1D circuit. It's a Clifford circuit, so it's simultaneous in polynomial time. So you have randomness in J and H with some probability. And now you have to make a choice. You rotate space to time. So we rotate X and T with each other, but keep Y same, Y direction same. You have to make some choice. So we made that choice. And the cool part here is that the rotated circuit is no longer now some non-Hermitian Hamiltonian. In fact, it's, I mean, not like some generic non-Hermitian Hamiltonian like in the previous case here, but here it's actually precisely just only unitaries and only force measurement. So it's much more closer to the original this works in this field where you have force measurements and unitaries. So that's what happened in this case, and it's also Clifford modulo this force measurement. So you can again simulate both circuits, and you again find a transition in both circuits at the same point from volume to area law. So the one side it's volume law entanglement, other side it's area law. You're in 2+1D, so the volume law is L square, and area law is L, and they match up neatly at the same critical point. So you can, yeah. So that's what happens in this circuit. So in one side of physics is precisely because of localization, because of the fact that you have randomness in space, and you're time periodic. On the other side, it's physics is that of it's projection. So the quantum interference maps to physics of Zeno effect under rotation. So that's the kind of general message over and over again. So the final thing I want to mention is this. So first two examples were free fermion and Clifford circuit. Now let's consider like an interacting system where we can't solve it, but we can do numerics. So we take this well-known model which has been used many times before for studying Floquet MBL circuit in one dimension. So you have some randomness in the Z. And then it is known that there is an MBL to thermal transition, at least on small system size. That's what you see. Of course, we can all still debate whether MBL even exists and so on, but at least at least in small system, there is two very sharply different regions, and okay, this is known. So now you rotate it again. You find two different regions. With one side is area law, other side looks volume law. So the rotated circuit is non-Hermitian and disordered in time direction, but translation variant in space because it inherits the time translation of the original circuit as spatial translation. So to see this more clearly, this transition, it turns out to be here. Maybe Mr. Last gave it. It's kind of not as sharply. Maybe looks like, but there's one interesting protocol you can use, that is introduced by Hughes and Goulans, which is so take your this non-unitary circuit which has projections or maybe non-hermeticity, although they only study the case of projections. And then couple it to a reference qubit. So you have some reference qubit and couple your circuit to it and study the purity of the qubit. What they found was that in the Zeno phase, where you have area law entanglement, the reference qubit purifies itself in order 1 time. So you can look at the purity of the reference qubit, like trace flow square. And in the non-Zeno phase, it purifies in exponential time. So that was the main point of their work. And so we thought, okay, let's just use this protocol. Maybe it will be helpful to detect this transition. It becomes actually extremely sharp distinction in this protocol. So we study the purification dynamics. And this is the insight is the purification time. It's order 1 in one phase. Other side, it really grows very fast on the system size we can access. It's suddenly super linear. Hard to like exponential in such small system, but it grows very fast. And the purity you can see is 0 in this side at if you choose some, I don't know, time, it's 0 at the initial time, and in the second one it's maximal, like log 2, and you can see the distinction in the two phases. So when you look at these figures, at least it's kind of they do jump at you at a level. I mean, it just in one phase you see this purity just goes exponentially to 0 very quickly. You can just see this is on the log plot, a y scale. You can see, so it's exponentially decaying purity. On the other side, you see these plateaus. So when you're in this volume law phase. So in fact, I would say the signatures of this transition in this rotated non-unitary circuit are much sharper than the original MBL circuit. So this could be some hint of maybe understanding MBL perhaps better because you're effectively studying now a very large system for a short time in the MBL system, right? That's what you did by doing this rotation. So that's instead of studying small system for a very long time. So it has this maybe some use, this way of thinking. So just to make sure, I think we started a bit late. So how much time I have?
Yeah, you can take 5 minutes, I guess.
Okay, I think I probably won't need, but at least I'm not over time. That's
no.
I'm mostly done, I think. So I think
you're good. Yeah.
I think this is basically the last slide, if I remember correctly. So the one question you can ask is there mapping of correlation functions between the space-time rotated circuits? So we were specifically interested in a correlation function which just maps in one system to the another system without any, I don't know, ambiguity. So then we looked at these kind of funny correlation functions. They look maybe standard if you just look at the part integral, but they are really not. So just insert two operators at x1 time, x1 t1, x2 t2, and e to the power is, because there's no time out. So they are actually instead of trace of u dagger o u o, they're like trace of u o u o. So these are like, if you like, half Keldysh. So you always go forward. You never come back. So, so you can show that this kind of correlation function in the unitary circuit maps exactly to some correlation function in the non-unitary circuit. So, so why is this useful? We can show that in the unitary circuit, if the system has a many-body localization transition using this L-bit picture of MBL, this correlation function precisely measures how well defined your L bits are. Basically, the coefficient of the overlap of your physical spin with the L bit, the quasi-particle weight, if you like. So it will have singularity in the MBL circuit, this correlation function, and you can detect it. Small system numerics. This is what you find, but by construction, it is equal to a correlation function in the rotated circuit. So the rotated circuit also hosts a correlation function which is also singular whenever there is an MBL transition. So this was at least for us useful, this way of thinking about it, to kind of argue singularities in one imply singularities in the another, and so on. Yeah, and as I mentioned, is it's nice work by Matthews and collaborator where they actually mapped entanglement also. But there, if you try to map entanglement, you get some extra terms at the boundary. And hopefully, I think Matthew will discuss. And there's a lot of nice physics, and I think they basically argue that the spatial dependence of entanglement becomes a time dependence of entanglement in other case, and so on. But here we just studied just this kind of correlation function, which is 2 point. All right, so so that's the summary, and so that you have spatial disorder unitary system, and then you rotate it, and then you get a in the original circuit you perhaps some localization physics, localization transition, and it becomes a this quantum Zeno transition in the rotated circuit from volume to subvolume. That's the main message basically. And then I mentioned this half-Keldysh correlation function, and there are a lot of open questions. One is obvious one, that since we can solve some of these things basically in polynomial time, I strongly think that there is a simple field theory description of some of the transition I described today. So we are working on that. That would be nice. And especially these free fermion ones. Yeah, so that's one direction, just thinking about. And second thing will be this half-Keldysh correlation function, I think has interesting kind of use in field theories and so on. So we are also thinking of that. And one last thing I wanted to mention, that at least it's a very reasonable conjecture, at least to make, that if a circuit is, if the rotation of a circuit gives you a unitary, it doesn't have to be same unitary, it could be any unitary. Then it's reasonable to conjecture that the original circuit doesn't have MBL physics. I mean, cannot have MBL phase. So can one prove that analytically? But if you take that as a I don't know, as a conjecture, then you can obtain interesting conclusions about systems which look fairly random in various ways and do not have any MBL physics. And yeah, I wanted to show me a couple examples, but I think I didn't get to make those slides. But let me just leave that for another day. So yeah, so that's it. So I think so I'll stop here and take questions.
Thanks, Tarun. Thanks for wonderful talk. So now, I mean, is there any question from the audience? Please feel free to ask.
Yeah, I have a question again on the similar, like the fractal laws. So is there, is the coefficient in some sense like universal? Because, if you're expecting an RG to hold, you'll expect some sort of, robustness to the fractal law of the
that's a great question. So this, it turns out the coefficient of the the fractal. First of all, it's a multifractal phase, so there's not just one exponent. There are infinite exponents for even at a given point in the phase diagram, depending on which power of, for example, wave function. Like very much like the when you have a transition between, let's say, localized and delocalized in the Anderson transition, there is a multifractal wave function. Here, the cool part is it's unfine-tuned. That's in fact the main message. It's not fine-tuned fractal. It's unfine-tuned, but the coefficient of this the fractal exponent actually changes continuously in this phase diagram, and that you can also kind of argue. So it's not. It's more like if you kind of from a very purist point of view, this is like infinite number of fractal phases, if you like, very much like, I don't know, like we think about low temperature phase of XY model as not a one phase, but infinite number of phases. So it's a bit like that. And we don't have a RGA picture right now. We are still trying to understand it. It's not as, I don't know, as straightforward because it's real time rather than imaginary time. Doing RGA is somewhat tricky. But the exponent does change continuously, very much like low temperature physics of some XY model, for example. So it's not pinned to any number. There's one on that note. This model has actually the original RBI model has this duality between K space and real space. This model also has that duality. There's a self-dual line. Along that line, you can tell what the exponents are. So if you go away from that, they change. But along that self-dual line, which is almost like a diagonal line here, so forget that line. I don't know. Maybe I don't know whether I think this one might be it. The way it is plotted, I don't remember. It's factor V2 somewhere, but there's exists a line along which, yeah, I think this is a self-dual line. So along that line, you can just this dashed one.
That's does that appear from the fact that because of its self dual the time circuit is also unitary and not projecting or like something like that, something correctly?
Sorry, what is so this is everything is all of this discussion is for the unitary circuit. The non-unitary circuit, we are not, I mean, David's group is not studying non-unitary circuit. They are only studying the unitary circuit. The non-unitary circuit, of course, has this transition which I discussed, but that's not, we are not studying that experimentally.
Okay, yeah, okay, yeah. Like okay, yeah. Cool. Thanks.
Right. Can I ask a question?
Sure.
Yeah. So so I'm not an expert in what you're talking about. Could you go back to your previous slide? So you just said that this in the fractal phase, this exponent actually is a continuously varying exponent.
Yeah, as far as we can tell, yes.
So is this something like a Griffiths type physics?
No, it cannot be because in a quasi-periodic system there are no rare regions.
Okay, so there's no rare region effects that are happening here. Okay.
Exactly. That, and as I emphasized earlier, that it's not because of rare region physics like in the MBL physics, like in the MBL phase, sometimes we can get fractal law in the exponent for the time growth of entanglement, right?
Right.
Like t to the power a. This is not that physics. That's why it's more, I don't know, I would say new. So so this one is, it's really, as I showed here, there's a wave functions are fractal-like. You can go to the wave function, individual wave functions of the Floquet unitary, and zoom in. This is for example, this is a wave function, right? You can look at a small part of the wave function and zoom in. It again looks like same shape. You can keep doing that over and over again. It looks fractal. So that's why, yeah, it's nothing to do with Griffith's physics.
Thanks.
Tarun, I have one question. See, in the when you rotate it in particular way, this space-time rotation, what we now see the dual. So you are able to get all these phenomena. Instead of this type of rotation, if I go for other type, for example, partial transposition is one type of rotation. I'm just giving an example. So do you expect or do you have any comments on other type of rotations?
That's a great question. I haven't done. I've tried playing out a little bit. I haven't done a whole lot so far. I expect there will be stagnation of the transition if you do some other kind of rotation of some other. I mean, it will be. I mean, generically, again, partial transposition will give you some non-Hermitian. I mean, not non-Hermitian. I mean, it will give you some something which is not
unitary.
Yeah, it'll be it won't be unitary. So then I would expect it will also have some similar physics, but I don't know. I haven't studied it.
No, the way I should have the similar question is that so why do you look into this particular direction?
Yeah. I can tell you why I looked at this one,
Yeah.
because I'm thinking again from a more field theory point of view that in the field theory, this rotation keeps Lagrangian local. That's why. So at least I have some very simple picture. If I do something more brutal, you mess up the whole locality of the system. Here, it's a local circuit in the rotated circuit. So it has all the nice properties, for example, as light cones and so on. Apart from maybe some okay, I take it back. If it's a non-Hermitian circuit, then doesn't have to be light cone, but at least it has. If I look at the Lagrangian, the non-Hermitian terms are local. Let me put it this way. So very much like when you think about atom loss, for example, right? And for example, I don't know, like for example, this model I worked by Shawchens and collaborators, right? It is we know a lot about systems which have imaginary local terms. For example, the most famous example is Ising model with I phi cube term, which is what this is, essentially at low energies. So that, as you know, you can even access that transition using RG, using epsilon expansion and so on. So there are a lot of nice things happen when you have a local Lagrangian, even if the physics is not Hermitian. So that's why at least I find this more somehow pleasing.
Okay.
Yeah.
Thank you.
One question?
Yeah.
So there's something I don't understand, because in the unitary version, the fact that the circuit is time translational invariance is crucial because you need that to have localization.
Right.
On the other hand, in the non-unitary version, the spatial translational invariance doesn't seem to play an important role, at least naively. No? So
yeah, it doesn't.
why,
But here the logic goes from the MBL side to that side. If the MBL, we are starting from circuit which have MBL transition, and then getting circuits which are so may I ask, okay, let me destroy the MBL transition on this side by adding some randomness in that time direction also, right? You can ask that question. So then you will lose one of the phases here. You will, because here you lose the volume, here you lose the MBL phase, here you will lose the area law phase in the rotated circuit. So that's the answer to your question. So because at least the focus for us was to study circuit which have two different phases. So
all right, no, just naively, I didn't see why in the non-unitary version, I didn't see why this would destroy the area law.
So we have
apparently does.
So I don't know in general answer, but there are examples where you can calculate analytically. So we can show. So there is example in our appendix where we can show if I break the time translation circuit of the original, you will get rid of the area law phase here, always with no volume law. So that's for the free fermion, you can show that analytically. So it's not in the slides, but you can look at the paper.
Yeah. I think Ranjan, are you there?
Yeah, I am here. Yeah.
Okay. Yeah. Thanks.
Okay. So again, thanks Tarun for wonderful talk. So next speaker is Matteo.
Hello.
Hi, Matteo. So can you start sharing?
Yes, one
the
second.
Yeah.
I'm sorry, I need to grant access to.
Yeah. No, it's fine.
No, do you need any access? Normally, it doesn't ask any access.